loud. All right, welcome everyone to today's CCAM presentation. I'm especially pleased to open today's presentation by having our undergraduate and graduate students presenting. It's a very, very special occasion when our students work on projects that are relevant and timely, and considering that they go out of beyond the curricular definition of course topics and so forth, and spend a lot of time learning new materials, and then try to apply those learnings in the context of relevant and meaningful and timely project. So it's glad to see our colleagues and our students. And today we have 4 students who have worked on analyzing some data from COVID-19. I see them, as I see them, I present them. Caleb Pena is our undergraduate student. He's graduating this semester, I believe. Is that right, Caleb?
That's right.
Seth, all right. Seth, also, are you graduating this semester, Seth?
Yes, correct.
Graduating this semester. Gwen is graduating next semester.
Yes.
And Cameron, who is here, is our graduate student from the Applied Mathematics program. Welcome, Cameron. And I know that you have a set of slides available, if you don't mind sharing it with us. So without further ado, let's welcome them to their presentation on a few strategies for the statistical modeling of COVID-19 data.
Thank you, Dr. Beceta. Hi, my name is Gwen, and I'm going to begin the presentation. Okay, so the coronavirus has been a major topic for this year, and it is a critical concern for our public health. We are constantly bombarded with information about COVID, either hearing it in our daily news, reading it in articles, or just hearing different information from family and friends. So this disease has become a huge part of all of our lives, and it has impacted us every day in more ways than we could have ever imagined. So to begin, in March of 2020, the World Health Organization declared the novel coronavirus, or COVID-19, a global pandemic. It was called a pandemic mainly due to the speed and scale of the transmission of the disease. Currently, there are over 69 million cases and 1.5 million deaths worldwide, and these figures still continue to grow. So it has been a little under a year since the start of these changing times, and we are in desperate need for some answers to help solve this growing problem. So in our research, we want to be able to predict the impact of the coronavirus, which in turn can potentially save lives. We will be doing this with big data by using machine learning and statistical models. So before I get into the research, I would like to take a step back and just briefly explain the history of the coronavirus. So just a tidbit of how the coronavirus got the name COVID-19. If you look at the name coronavirus disease 2019, it can be abbreviated, as you see in the color red, as COVID-19. And there have been many theories and stories on where this disease began, but scientists believe the coronavirus began in wild animal markets, and they have strong evidence that the virus originated in bats. So various species of both wild and domesticated animals are kept alive in close proximity within these markets, which unfortunately helped the disease easily mutate and spread to humans. So when did it come to the US? It is now believed that the virus came earlier, but public health agencies detected the 14 US cases of the coronavirus disease in late January through February. These came from 6 states that included people who came to China as travelers. The outbreak appeared to be contained through February, but then people who did not travel internationally became affected. So from there, the disease accelerated rapidly, and it became widespread due to the incoming travelers from different countries, large gatherings at social events, and limited testing during the critical times. So at this point, according to the CDC, there have been over 15 million cases and over 280,000 deaths in the United States alone within the first 10 months. The first case was reported. So overall, like I said, worldwide, there have been over 69 million cases and over 1.5 million deaths from this fatal disease. These plots from from Johns Hopkins are showing the accumulation of number of cases. So the US is shown in green and we are leading in the number of cases. And additionally, in this plot is showing accumulation of the number of deaths worldwide. And we are also near the top as well in the world. So the world has gone through many different pandemics throughout history, such as the Black Death from the 1300s to the Spanish flu during the First World War. So what is different about the coronavirus? So before I get into this section, I just want to clarify I am no biologist. So I will be talking about the highlights of the coronavirus briefly for us to get a better understanding of this disease. So the disease is spread between people who are in close contact with one another through respiratory droplets or small particles. So these small particles are produced when an infected person coughs, sneezes, talks, or breathes. And additionally, these droplets can also land on surfaces and objects and can be transferred by touch. The coronavirus, also referred to as SARS-CoV-2 due to the similarities of SARS and the severe acute respiratory syndrome from 2003, primarily targets the lower respiratory, causing fatal respiratory illnesses. Next, the virus inflames the airways within the body, which contributes to lung complications such as pneumonia. This creates breathing difficulties, and in sometimes severe cases, patients can be required to be put on ventilators to help them breathe to maintain a supply of oxygen. So it primarily infects cells, and it does so by replicating deep within the lungs. So the outer spike protein, the spikes you see coming out of the membrane in the picture to the right, latch onto specific receptors on the surface of the cells in the respiratory tract. So from this virus, it fuses onto human cells and it mistakenly assigns, mistakenly assigned as proteins, which causes the virus to replicate and make millions of copies of itself, causing the illness. So this just gave us a brief overview of the history and the background of COVID. So if you would like to learn more, I know there are lots of resources about COVID, and I'm just going to provide some sources for those of you who are interested in furthering your knowledge on this lengthy subject. So the center sponsoring this talk, CCAM, has devoted a page on the Cal State Fullerton website to some amazing web pages, resources, and more articles. And there are plenty of pages referencing to predictive modeling, scholarly work from Cal State Fullerton faculty, and data resources. Furthermore, looking more into literature reviews for more examples, this research in this bullet point is using social media data to find if there are correlations with the prediction of the transmission disease, mainly looking at user behavior. And then while this other research is looking at artificial intelligence, or AI, and they can do various things such as identifying early detection, tracking the spread of the virus, and helping to determine useful drugs for the treatment. So like showing here, there are endless amounts of articles covering many aspects of COVID, and each one is of a great deal of help. So now I'll be getting into our research. So this leads into our own objectives. So what is our objectives? How can we help? So in our research, we are showcasing simple statistical methodologies of COVID-19 with data that is relatively accessible. So we utilize machine learning statistical models, including time series models, to address two main goals. So first, we want to predict and track COVID cases by county. So by being able to predict the number of cases ahead of time, this can greatly help healthcare organizations readily prepare to accommodate for the newly infected. Second point, we wanted to classify the counties based on their COVID data. So by identifying distinct features that cause a significant impact on our model, this can help create decision-making technologies to help handle this virus a little more. So before we begin in our research, we need to find some data that best fit with our objectives. We needed data looking to COVID cases, the number of people infected, COVID deaths, the number of people dying from this disease, and mobility data since the virus spreads rapidly through contact. So for this study, we extract freely available mobility data from two sources, as well as COVID data from a third. So the two sources for mobility data are from Google and Apple. And the third source is from USA Facts, which looks into COVID-19 infections and deaths. Lastly, from this source, lastly, we created these sources for 2 data sets. The first one is consisting of the 2 most populated counties in each state, and the second one is looking at the 7 Southern California counties. So in these next slides, I'll be going more deeply into explaining these 3 sources and how they work. So first, Google data. So Google data is available by community mobility reports. So these reports aim to provide insights into what has changed in response to the policies. So what are in these reports? These reports show movement trends over time by geography across different categories of places. So these categories include parks, grocery stores, transit stations, retail, workplace, and residential. These categories are grouped with places of similar characteristics, such as grocery store and pharmacy can come together and be considered essential trips. How's the data collected? So Google collects aggregated data, meaning from multiple sources, and it focuses more on where people spend their time. So data is collected from your phone when you give permission to share your location under Google Location Services. And what does the data look like? So each category has a different metric. So for each day of the week, in order to measure the metric, it creates baseline days. So baseline days represent a normal value of that day for the week. But more technically, the value of the medium, this value is the median value from the 5-week period of January 3rd to February 6, 2020, before the widespread of the virus. So to interpret the data, looking at the visual, each day of the week is given a number like this under a specific category. So for example, this is looking at retail, grocery, and park trends. So this number can be reported as a positive or negative percentage, but a special note is to not look at these numbers as averages, but rather we can interpret it as looking at -18, for example, -18%. We could say that on this particular day, there was an 18% decrease from the baseline in retail. So second, Apple data. The Apple mobility data is very similar to the way that Google data works, but instead of using Google locations, they use Google Maps. So how do we track these? How do they track them? Apple tracks transportation of all types, such as driving, walking, and transit. And how is it collected? The data is collected when someone puts in a request, such as asking for navigational directions. And then similar to Google, to interpret the mobility data, they created a baseline day, but it's only for 1 day of January 13th. So looking at the visual here of what the data looks like, the data is reported a little differently than Google. So Google's metric was a positive or negative number, but and it determined the increase and decrease from the baseline. But while Apple metric, shown in figure 5, shows the metric to be a number such as 109.61 or 95.25. So we can interpret it the same way as Google. So for example, on January 15, 2020, there was a 9% increase in the baseline in walking when you see the number 109. So for the last source, the third source, we use USA Facts in our data set, and it tracks COVID-19 data by state and county. So on this site, we can follow new cases found in each day, total number of cases and deaths in the US. And additionally, we learn about the locations and geography, so we can understand the social economic factors and features. Okay, so we just talked about the 3 data sources: the mobility data for Google and Apple, and then COVID-19 rates for USA Facts. So how do we work with these sources into one data set? So short answer is we use data wrangling. So our goal is to be able to weave these 3 different sources together into one data set, but this requires some thought and programming. But first, we need to take a step back and consider some important facts. So we need to understand the time range of the exposure of the symptoms. So according to the CDC, this process takes approximately about 2 to 14 days. Next, it's imperative to know how long it takes for the symptoms to develop. So this period is shown to be about between 4 and 5 days. Next, when are you most contagious? Research suggests that people are most contagious in the 48 hours before symptoms develop, and they remain contagious for up to 10 days after onset symptoms. So we need to recognize the importance of those facts I talked about previously and apply that understanding to our data set. So in order to adjust for those timeframes of the disease, we take a naive approach. So we know we have n number of data points for how many cases reported, and x is the number of cases. So from the points on the previous slide that I make, the cases that are reported today are influenced by past interactions. Thus, we create the new variable y, where y is summing up the x cases, but shifting it 4 days back to account for the incubation period, since it usually takes about 4 days for someone infected to show symptoms. So just an example of how this works, x still represents the original data and y is the approach from the previous slide that I just talked about. So we can see from 412 that the sum of the cases from 4.1 to 4.7 is a total of 18 cases. So this is an overestimation of the true case shown reported from 412, which is showing 2 cases. But we now have condensed 7 prior days of information into one variable. The attempt is to capture the number of people who were contagious last week. So for mobility data, since we do not know which days people are infected, who's infected, and where they travel before they develop symptoms, we use the same approach. So using the naive approach, this is taking the averages of all the parameters in the data set for the 7-day period ending 4 days ago. So with this example, again, it is very similar to the idea to the cases, but for the mobility data, we are taking the averages of the 7 days. So for 412, again, we are summing up the mobility data, which in this case equals 18, and then dividing it by the number of days, which is 7. So for this data set in figure 6, we spent a great deal of time coding to be able to gather these different types of data from multiple sources to bind them together into one. In the end, now that we have considered those important aspects and adjusted for those changes through coding, our data sets are now uniform. And as an outcome of our data wrangling, this figure is showing the final result of our data. So now I'll be handing over to Seth to talk about our methods and results for prediction.
Thank you, Gwen. Okay, yes, so we're going to get into our methods and results portion of this presentation. And since we have 2 main goals, our methods and results can be thought of as being split into these 2 sections, which would be our prediction methods and results, and then our classification methods and results. And we're going to go ahead and begin this portion of our methods and results in regards to prediction first. So the methods we applied for prediction are ridge regression, lasso regression, Poisson regression, and our time series model, generalized linear auto-regressive moving average model, or GLARMA for short. So let's take a moment to discuss shrinkage and regularization techniques. So when dealing with and modeling a data set as large as the one we are, there are 2 common issues that can occur. The first being the dimensionality of the data set itself. And by this, I mean a large parameter space or a large number of predictors we have to estimate compared to the number of data points we have or observations. And the second issue would be high correlation between these 2 predictors, and thus resulting in a lot of collinearity in our data set. And both of these issues result in very biased estimation of our parameters. So to address this, we're going to use a few regularization techniques. And the main idea behind these techniques are to introduce some bias to our models to reduce the variance and thus the uncertainty of our estimations. And in this process of introducing bias, we are effectively shrinking our parameters towards 0. And in the most extreme case, we can actually make our parameters equal to 0, thus eliminating its corresponding predictor and reducing the dimensionality of our data, which was our first issue. So the 2 most common shrinkage methods are ridge and lasso, and we're going to go ahead and look at them here in a linear model context so that we're able to differentiate what's different between these 2 models and our usual linear regression, although they are available in a nonlinear format as well. So the key difference here would be the final term in both cases, which is the penalty term. And this is what is going to introduce our bias into our betas or our coefficients. And we are going to control this amount of bias being introduced via the red parameter lambda there. And as we increase this value of lambda, we effectively are increasing the amount of bias being introduced. And if we make this lambda equal to 0, we effectively have our usual linear regression model. Now, the key difference also between these 2 methods would be that ridge shrinks our parameters towards 0 at the same pace, while lasso does so at a different pace. So we effectively perform model selection in conjunction with this process. And so how do we choose our optimal lambda, right? So we're going to choose our lambda based on its associated mean squared error. So if you look at both of these examples, moving from left to right, as we increase the value of our lambda, we effectively increase the amount of bias, which is the black line, and in doing so, decrease the amount of variance, which is the green line. And while we do this process, we are going to withhold a certain amount of data, which we call test data, and we look at each value of its mean squared error of differing lambdas at different moments, and thus we choose our optimal lambda, which would be the lambda associated with the least mean squared error in these cases. And this process is a cross-validation process. Okay, and then we can go on to our next method, which would be Poisson regression. And here we let our response follow a Poisson distribution, and our response in our case is the number of cases. So we let follow, yes, a Poisson distribution with intensity lambda, and lambda here again has a relationship with regression. If you look inside the parentheses, you can see our alpha would be our intercept and our betas would be our coefficients, where x is our predictors. And this relationship is modeled via EXP. So if we took the log of lambda on the left, we would have the resulting usual regression on the right-hand side. And now that we have this relationship built, we're able to estimate our parameters, which are our coefficients, via maximum likelihood estimation. Now moving on to our time series model, we once again allow our response to follow a Poisson distribution with intensity lambda sub t, where t stands for time. And it's again an exponential model of predictors. And so this system illustrates this model nicely. The key difference here between this method and our most previous would be on line 2. We see we have a third term, a new term. And this is the autocorrelation, or the relationships within the data sets. And this comes from two sources or two terms, which we see on line 3. The first term would be our auto-regressive term. And this essentially allows our model at any time to consider some of its previous observations up to some lag p. And the other term would be our moving average term, which essentially smooths or averages the data through some window as we move through time to some lag q. Thus, this is called a generalized linear autoregressive moving average model of orders p and q, where p and q are lags. And we choose these lags by testing the most significant lags found via the autocorrelation function and the partial autocorrelation function. And we're once again able to estimate our coefficients via maximum likelihood estimation. So now let's talk about how these methods compare. So we're going to look at them and how they compare across our 7 Southern California counties. And here we have our comparison of performance via root mean squared error. So since we're talking about error, the higher the value, the worse the performance. The lower the value, the better. So right off the bat, we see that our Poisson regression does the worst, especially so in Los Angeles County. Coming in second would be our Lasso and Ridge. It's hard to make out on this diagram, but Lasso does out-edge Ridge slightly. And finally, we seemingly have our time series perform best across the board. However, if we take a closer look between the Lasso and our time series model in the mean squared error context, we see that there are 2 counties or cases where our Lasso model seemingly does better than our time series. However, since we're doing a comparative analysis, it's prudent for us to take a closer look at what's really going on in these 2 cases. So here is our Riverside County, Lasso on the left, our time series on the right, and blue is our actual observations, where red is our prediction. And we're able to see that the Lasso model achieves this lower score in mean squared error because it's estimating more of the average over time, but it's not really actually estimating the actual predictions quite accurately, where our time series model does do a slightly better job. However, the key takeaway to take from these 2 plots is the amount of observations here, which are 0, right? So this may be a result in the procedure that they are reporting cases in these counties. But either way, it's difficult for any of our techniques to model such a data set like this. Moving on to the Ventura, our other case, we see a similar story, excess amount of observations which are 0, and thus the Lasso achieves a lower mean squared error by estimating the average over time. So now let's talk about how these methods compare into another county which doesn't include such a high number of 0 observations. Specifically, we're going to look at Orange County, as this represents what our usual counties look like across our data sets. So here's again our worst performing model as a baseline, and this is the Poisson regression. And we see it's not quite capturing the trend or predicting the cases quite accurately. However, moving on to Ridge, we see that now we're starting to get the model to trend nicely. although our cases at any given day aren't too accurate yet. Moving on to Lasso, there is an increased performance upon ridge, still modeling the trend nicely, but still not too quite accurate on any given day. And finally, we see our time series model where now we're modeling the trend very nicely, and in some cases predicting the cases very similar. You see after the month in July, we see there's a slight gap in our predictions and observations. However, if we move through time and look towards the end, where we're currently experiencing this new spike in cases after November 1st, we see our predictions and our actual observations are very spot on, very precise. This makes sense, right? Because this is a time series model, it's a history-based model. So now let's take a step back out of Southern California and consider the national trend of cases across the United States and how our models can capture this trend. But before we get into our data, let's take a look at the aggregate sum of cases across all counties across the United States provided here by usafacts.org. So we're able to get an idea of what this trend looks like. Now getting into our data set, this is the top 2 most populated counties data sets, where the blue line is the average reported cases across these counties, and the red is our prediction via the model. And we see that both the observations and our predictions match the national trend pretty similarly, pretty closely. However, when we split this data set into counties above and below the 90th median income percentile, we see that the bottom 90% still follows this trend. However, the top 10% most wealthy counties have a slightly different trend. Now, since our model is able to predict these trends in both cases very nicely, we're going to go ahead and overlap these trends and compare and see what they look like. So here we have the red line, which would be our most wealthy counties. And we see it does have a increase in cases in the first few months, but then it dies off, having a differing trend. Now you may be thinking that these two groups may have a slight difference in population, right? The most wealthy counties probably are going to have less people on average than the bottom half. And if you're thinking this, you are right, actually. Moving on to the next slide, we can see the mean between both of these groups. And the bottom 90% does have a larger amount of population on average. However, now I do have a plot for you for these skeptics as well. Here we scaled our cases by population, where red is our most wealthy counties, and this is cases per 1,000 as in population. And we see that these trends still do persist. So these trend lines were made artificially via the division in our data set. And with that, we're gonna go ahead and switch our gears over to classification. I'll hand it over to Caleb.
All right, thank you, Seth. So I don't want to spend an awful lot of time talking about the different methodologies that we used, since I know that a lot of the people in this room are math professors or have some other background in machine learning and are familiar with these terms. But we want to start by just giving a little bit of an overview of the kinds of methods that we use to perform the classification. Before I do that, though, just a quick answer the question, why are we actually performing classification? What's the value that we're gaining from that? And essentially, the reason we're doing this exercise where we are essentially putting a blindfold on the model and asking it to identify what county the data comes from is because by doing that, we can have a better understanding of how the variables interact with each other, how mobility and COVID data comes together to work together to make these predictions. So variable importance is a big piece of that, but additionally, by being able to break this up on a county level, it gives us a better idea of how COVID-19 impacts different types of populations. And we're narrowing our focus once again here just down to the 7 counties in Southern California. But that gives us a nice way of we can treat it like a microcosm of the rest of the country. There are certain counties in Southern California, like Imperial, that are much more rural. And there are others like LA and Orange County that are much more urbanized and industrial. And because of that, because the differences in income levels, number of individuals per household, we can understand better how COVID-19 is affecting these different types of populations. So the methods we use for this exercise are logistic regression, linear discriminant analysis, quadratic discriminant analysis, k-nearest neighbors, and neural networks. And I'm going to give a brief overview of each one that we used. First of all, logistic regression. The simplest case of this would be where you have 2 different categories that you're trying to distinguish between, to label, and one predictor. And what this illustration here with this graph shows is why something as simple as linear regression isn't going to be useful. And take those two categories and assign them certain numbers on a discrete scale. But once you try to make predictions using linear regression by drawing a best fit line, you get meaningless output. You get negative values, and there's no real way to interpret it directly. On the other hand, if we go to the next slide, we can see what happens when we try to apply a transformation to the response variable. And our goal is to be able to find some transformation that binds the response between 0 and 1 and that is continuous. If we can accomplish that, then we can essentially interpret the results of the model as a probability. And that lets us do classification. A really nice candidate for this, a nice transformation, is the logistic function. And it essentially allows us to take the log odds of a particular observation landing in one category or another, and fitting a best fit line to that instead. And then we can reverse the transformation and get this nice S shape that we can use as essentially the probability of belonging to case 1 or case 2. So how do we find these betas that we're using to fit this best fit line to the log odds? The standard way to do it is using maximum likelihood estimation, just like with linear regression. We are currently in the process. We have some basic code in place to use a different method to estimate these parameters using Bayesian techniques, using non-informative priors. I don't want to go in depth as to what we're doing right there, because we don't really have results that are ready to show you guys today, but that is in the near future. We should have results showing what happens when we classify using that method. So once we do have these different probability values, we can take some threshold, generally 50%, and use it as the way to determine whether or not we belong in class 1 or class 2. This can be easily generalized to different cases. We can generalize it to an instance where we have more than one predictor. All we have to do is add an additional variable and an additional coefficient to that best fit line. In this case, it wouldn't be a line, it would be a hyperplane, but we're just extending it out linearly. And if we want to extend it to the case of more than 2 categories, we can do that by looking at multiple pairwise regression. The second method that we used is linear discriminant analysis, and this is a little bit different. Similarly to what we were working on in terms of using Bayesian methods to estimate the parameters in logistic regression, we can also use Bayes' theorem here. Essentially what we're doing is we're treating the probability of a particular data point belonging in class 1 or class 2 or class 3 as essentially being proportional to some prior distribution and multiplied by the likelihood function. So what we need to do is to find some type of estimates for both of these elements of that equation. We need an estimate for the prior probability and an estimate for the likelihood function. The prior probability is fairly simple. With linear discriminant analysis, what we do is we just treat the sample proportion as our prior probability. We just take the total number of observations in our training data set that belong to the class we're interested in, and we divide it by the total number of observations of all classes. For the likelihood function, we do something a little bit different. We make the assumption that the data that belongs to any given class follows a Gaussian distribution, a multivariate Gaussian distribution. And a Gaussian distribution, that bell curve that we're all familiar with, has 2 different parameters that we need to estimate. The first would be the mean, the sample mean, which we use to estimate the population mean. And the second would be covariance. And what's special about linear discriminant analysis is that we make an additional assumption that the covariance matrix is the same between all the different classes we're interested in this case, all 7 counties. On the other hand, if we go to the next slide, if we are looking at quadratic discriminant analysis, we do everything we did with LDA. The difference is we don't make that assumption. We take the sample covariance from each of the different classes and use that as our estimates. And that gives us something slightly different. Instead of having a decision boundary that's just a line, we end up having a curve, hence the distinction in naming conventions, linear discriminant analysis versus quadratic discriminant analysis. Okay, so that talks about, that deals with the different parametric methods that we've been using. But we also have a handful of non-parametric methods. And essentially what we mean by that are methods that don't... Pardon me?
Someone's mic
okay.
is on.
That's fine. Sorry, let me just go ahead and continue. Non-parametric methods basically meaning that we don't make the assumption that the response follows some known functional form. And once we move away from those parametric modeling techniques, we get models that are harder to interpret. We don't have those nice coefficients that help us understand variable importance, but we get much more powerful predictions out of it. So with K and N, the algorithm is pretty simple, but you can see why it would be harder to interpret. What we're doing is we're choosing some value of K, and we're choosing some measure of similarity, something like Euclidean distance that lets us know whether or not two given data points are super closely related, very similar to each other, or very different. Then we take whatever data point we're trying to predict. We find the K most similar observations to that data point, and we classify it based on the plurality vote of the K most similar observations. So just to give an example of this, Gwen, if you wouldn't mind just highlighting a little section we were talking about before, if we were looking at one of these data points or a data point in this region, we can notice that the 5 most similar observations here, their plurality vote would be orange. We would classify it as an orange data point. Whereas if we expanded that out more, we might end up getting a plurality vote that includes more blue rather than orange. But that's the basic principle behind the K nearest neighbors algorithm. Okay, now for the final approach that we've been using, we're doing something called neural networks. This is a little bit difficult to understand. It's a more black box approach. Once again, very difficult to interpret in terms of variable importance. But the basic idea is we take each of our input variables, our predictors, and we place them over here on the left as an input layer. On the right, we have an output layer, a set of nodes that each represents the different classes that we're trying to categorize into. And then we have a certain number of hidden layers of nodes in between. And what we're essentially doing is creating some kind of network between them. Every single node in one layer is connected to every single node in the next layer. And it's connected by a set of different weights or coefficients. And once we get the initial values in the input layer, we end up getting a value out of the output layer that we use we interpret as a probability. And we fit each of those different weights using a system called backpropagation. Essentially, this is different from maximum likelihood estimation because it's an iterative process. We start at the output layer, we fit those alphas, we move back to the next hidden layer, all the way back to the input layer, finally at the very end. And because it's an iterative method, as you continue through the iterative process, the predictions tend to get better and better and better. So let's take a look at the actual results, since that's what I'm sure you all are interested in seeing, how this actually did at classifying the data points into different counties. Just like Seth was talking about in the section addressing prediction, we're focusing our attention on 7 different Southern California counties, because if we just let it grow to the entire country, there's just so many different counties that the accuracy is low enough that it doesn't help us to actually understand the variable importance. So just focusing in on Southern California, these are the results by county. And we notice a couple of things. First of all, right off the bat, we notice that the non-parametric methods, KNN and neural nets, perform the best. By far, we get with neural nets accuracy up in the range of 97–98%. But another thing that we can notice is that the results are not consistent from county to county. So if you look at Riverside County, for example, or Imperial County or Ventura County, those 3 counties, any method that you choose is going to do a pretty decent job at making those predictions. But if you look at, say, San Bernardino County or Orange County, there is a lot more, it's a lot more difficult to make those predictions, a lot more difficult to make those predictions using those parametric methods. So what we've done here in this slide is we've taken multinomial regression, the logistic approach we talked about earlier. We've taken the coefficients for each different county, and we've taken their absolute value, since what we're interested in doing is seeing the magnitude of the effect that each variable has on the classification exercise. So that's what you see on the y-axis. That's just the absolute value of the coefficients. And there's a couple of interesting things to notice. So the first is we have a handful of variables that have a low effect, but consistent across all counties. So that would be variables such as the number of grocery visits or pharmacy visits, retail visits, as well as requests of Apple driving instructions. And these are very useful because of that consistency. We can use it as a baseline against which we can measure other different events that are happening from time to time. And this spreads beyond just the coefficients. If we were to look at a graphic that demonstrates from time to time, like on a daily level, the total value in a given county, you would notice that grocery, Apple, and retail values don't move an awful lot. There is some fluctuations, but nowhere near as much as say, visits to parks, for example, which we'll show in the next slide. And that's valuable because we're able to identify when in a particular county something happened that's unrelated to COVID-19. If maybe there's something cyclical like a weekend versus a weekday, or if there's a holiday, a national holiday that happened, that can affect visits to the grocery store, but we can distinguish that from the effect of something like COVID-19. So with respect to these more erratic variables, we have things like usage of transit options, public buses or the Metrolink or what have you. And it's understandable why in certain counties those would be more impactful than others at predicting whether or not what county we're in, understanding the profile of each county. If you just take a look at the characteristics here, we can see that in Riverside or San Bernardino County, these are counties that are part of the Inland Empire. Not an awful lot of people using public transit there. Those are less impactful variables in order to determine what county we're in. Similarly, we might see something similar when we get to the prediction side of things. On the other hand, because those are residential areas as well, those variables are much more impactful at the classification exercise.
All right, so just to wrap it up, conclusion, I know a lot's been said. So just to take a step back. So what our goal was, we wanted to predict and track daily COVID cases by county through various methods and classify those counties based on their COVID data. So we used data consisting of the number of COVID cases and the number of deaths and mobility data. So back at prediction, we found that although basic in comparison of a more advanced techniques, our methods for predicting cases yielded high results. But which one performed the best? We found that GLARMA model was able to predict new cases very precisely. So Lasso was second and Ridge Regression was third, which wasn't far behind from Lasso, and Poisson was last. And the fact that GLARMA models created better results are not surprising, considering that the data is time series. So the GLARMA model captures the overall autocorrelation of time dependencies that exist among our data. Other machine learning models perform quite well, even though in principle they are not designed for modeling time-dependent data. So we suspect the goodness of their performance is particularly because the COVID data was quite noisy. Because as the data fluctuate, it can relate to certain factors. And factors such as states and counties have varying levels of observation and enforcing social distancing policies, as well as human behavioral patterns, which is the subject of Dr. Bishara and Dr. Baysetta's models. And lastly, since through our data wrangling approach, we had accounted for dependencies on the data set that might have made the use of our machine learning methods more efficient as well. Additionally, then we explored a bit more into the prediction model and looked at two most populated counties in each state. So using Lasso to predict the average of the new cases across the data set, we were able to mimic the national trend nicely. However, when we split up the data into counties above and below the 90th median income percentile, the trend at the bottom 90% still reflected the same trend of the national trend, and the top 10% had a different trend. So this means that the most rich, the top 10% counties, were affected differently from COVID. And then for classification, just a summary, each county has either the same impact or different impact based on their variables from the COVID-19 data. So some variables that were consistent within each county was the counties looking at to grocery stores, retail, and different requests, while understanding each county's different behaviors revealed a bit more information. So for example, looking into transit, LA would be much more heavy and impactful, while in most rural areas such as San Bernardino and Riverside, this information may be irrelevant. So in the end, this is telling us that across all counties, using different coefficients will be the best course of action when creating these models, and may require multiple models with different iterations to understand these effects. So for future work, there are many more ways we can extend our research and investigate even further in our COVID-19 data set. So for one, we continue to utilize the GLARMA model. So we applied the GLARMA model to transform the data, so we can apply it again to the COVID data that hasn't been blocked or condensed, since GLARMA can account for the relationship within the data, so maybe this can produce better results. Additionally, we are planning to expand more into Bayesian analysis in the future, as we have some code already in place. And lastly, we want to look further into the mobility data so we can explore trends into the most wealthy counties to see if we can spot any distinct features to understand their differences. So in the end, although the methods we used in this analysis are not quite complex, we were able to gain valuable insight into the nature of how the coronavirus affects us at a county level. And any furthermore, we were able to discover the interesting avenues we can further our analysis for the future. So these are our references. And as an end, I want to say thank you. Thank you, Dr. Becerra, for involving me in this project. Thank you, Cameron, our graduate student, for starting this research project. And thank you, Caleb and Seth, for being a great team. And lastly, a big thank you to our audience for watching and listening.
All right, let's thank our presenters. Thank you very much, guys, for that presentation.
guys.
Open the floor to questions. If you have questions for our presenters, please go ahead and ask.
Ask a question.
Sure, go ahead.
I guess maybe a couple. The zeros that I guess they were problematic, were they actual zeros or they were missing data?
Yeah, so they were zeros. Now, some of the counties we suspect what they would do they would report the cases maybe on the weekends on the following Monday, and thus they would report the zeros over the weekend.
So we could consider them missing, maybe. Is that true?
Yeah,
okay.
pretty much, yeah.
Okay. My second question was about, I guess, the performance. These are, I'm assuming, is overall performance, but was there any model that performs well with starting with the small data and getting trained over the time and kind of showing a better overall performance in terms of following the trend, or it was just a train and test set for using the whole data? I don't know if I was clear or not, but
I think I understand. So the time series model increased in accuracy over time, of course. Now the other ones, what we did was we trained in one of the graphics where we compared the accuracy. We trained each model with this associated Southern California counties, and then tried to predict these cases within that county itself. Overall, the Lasso model, as we saw, didn't perform as good as a time series in a small scale like that. But when we looked at the overall trends of all the counties, when we trained the Lasso model for, say, one county and trained it using the rest of the 99 counties, it was a lot more accurate.
Thank you.
I have a comment by Dr. Wayne Dwight. He is saying that we know that some of the discrepancies are because states reported This comment is from Dwight, sorry about that. We know that some of the discrepancies are because states reported cases from batches of several days of tests. I agree. I think, you know, it really is hard to figure out what it means by the number of infections per day. That's one of the mysteries, because there's obviously a gap between the time a person is being tested and the time that that person's test results are back. So in principle, this is a very complex data set. And due to the fact that that gap is not standard across even the state and between counties, adds to the complexity of the story. So totally agree with Dwight in that sense. Any other questions to our presenters? Dwight's hand is up. Dwight, go ahead, please.
Yeah. Hi, everyone. That was a great presentation. You talked a lot in your methods about assumptions of some of the models. Did you do any exploratory analysis to determine whether those assumptions were met before you started modeling?
Are you talking about the prediction methods or our classification methods?
Kind of both, right? There's some assumptions of, say, a Poisson regression model. There's assumptions of an LDA classification model. I'm wondering if you did any of those plots before you created any of your models to determine whether the assumptions that you were making when you created your model made sense.
Okay, on the prediction side of things, we didn't necessarily test the assumptions themselves, but comparing the results, it makes sense how the time series model performs the best because it's time dependent data. The Regression Lasso model is the second best because they do address the collinearity within the data set, because there is quite a lot with all our mobility parameters. And then lastly, the Poisson did the worst because it doesn't have a way of accounting for this sort of collinearity in the data set.
Okay, so you obviously did do some exploratory analysis to just see whether there was collinearity in the data set? Yeah,
quite a bunch.
Yeah.
Yeah.
And if I may add to this, that's a very important point you're raising, Dwight. Two things. The first thing is that we know this is a time series, no doubt about that. However, two things add to the possibility of using non-time series techniques for the sake of prediction. One, as they said, is noisiness of this data. The fact that cases vary widely, fluctuations are very hard to capture. The second thing is that they're using these methods, at least for this juncture of the story, predominantly for prediction purposes. So from a utilitarian perspective, the very aim is to see what goodness or accuracy they get back. That is, this is used less for inferential purposes, and thus, you know, while it's essential to check the assumptions in any application of statistical methodology, you know, it may not be one of their top 1 or 2 priorities here.
Right, because I'm especially thinking for the LDA, the reason that may have performed so awfully is because you're making an assumption of multivariate normal distribution with the same covariance matrix in each group. And if you check it and you find that the covariance matrices are way different, you should expect LDA to perform pretty badly.
And you're absolutely right. The expectation is that to some level, that covariance matrix might capture some relationship at a snapshot t between the predictors, right? But obviously, this is a moving average situation. And the good news about their time series method is that it actually creates a covariance structure that is a function of time. And then through those lags, they can actually delve deep into history both through autocorrelation terms as well as moving average construction, basically, essentially correlation through error terms of a Poisson assumption. So in a way, you're absolutely right. There are methods that you a priori know that they're not going to stand to it. But hey, you know, writing a code and running it is not that expensive, so why not? Any other questions for our wonderful graduate and undergraduate students? Dr. Bashar, please go ahead.
Yes. Hello. Thank you very much. Thank you for presenting us a really nice, well-structured presentation. Even if the finals is just next week, we really appreciate that. And so I have a couple of questions, and some of them it just maybe because I am not necessarily familiar with some of the methods that you guys have presented. So excuse me if they are very elementary. And so I have two of them. One is related to data, and the other one is related to the methods. So the first for data, I believe it was Gwen who presented. So so I was really excited about the mobility data that you guys have presented, but this excitement, my excitement kind of faded when you said the data were taken only if your navigation stuff is on, which most cases in most cases we don't. So I was wondering, but I mean, even if they are off, I suspect Google is still track our mobility. That's my suspicion. I might be wrong. So if the mobility is only, so the data is only collected if our location is on, how accurate do you think that is?
I'm not too advanced into that. It was more just the general idea was most people use that to say get directions from somewhere, so it would open that up. Or if you're trying to find say a pizza joint, you'll have to open up your the geography of where you are, so it knows where you are, so then you would be tracked. So you go, oh, this pizza place is over here. And so I might have not covered every aspect of it, but it's similar little nuances like that where you are needing your location to find friends or look up a direction for something. So you have to give permission for them to be able to see it. So it has to go through that kind of stream.
Right.
And then actually furthermore on that, I'm sure that these companies do track, location stuff all the time, but what we're given right now actually is only available for a limited amount of time. These companies, Apple and Google, made this data available because of the pandemic. So only because of their availability of this data, we're able to utilize what they're giving us.
Okay. If it's okay, if I can jump in here real fast, I just wanted to say that I think you're right, but I think one of the valuable things about having two different sources tracking the same thing, the Google data and the Apple data, it's nice that we can look at them and say, okay, even though the profile of someone who uses Apple Maps is different from someone who uses Google Maps, we're still seeing similar patterns over different periods of time. And I think that helps us get some idea that it might not be perfect data, but it's somewhat reliable.
Okay. Another question also related to data. So you guys have said that it's a noisy data, right? But by no means I'm very expert in data, but I think COVID-19 data is pretty good. I mean, at least as far as the cases and the number of deaths, it's almost like live, so you could track it. I think it's pretty good. So why you guys are saying it's noisy?
When we say noisy, consider those plots where we're plotting the actual observations of cases. We see that it's not really a straight line or a curve. It's very jagged and up and down. And those fluctuations and jagged up and down are what we refer to as the data being noisy.
Okay, so it's not because the data are not available, or it's not because, okay, I got it. So second, for methods, I'm not sure who presented. I believe it's either Seth or Khaled.
For prediction or classification?
Where you guys talked about KNN and neural networks.
Classification.
Yes. So I believe you guys have said, yeah, KNN and neural nets were the best predictors.
That's right. Yeah.
So, so the first part of my question is, so even if they are a little bit more accurate than the rest, do they have also the same, like as far as machine goes, like the timing in your machine? Is it more costly to do KNN and machine and neural network to gain a little bit 0.1 or 0.2 level of accuracy, or is it just much better?
That's a really good question. So Canon was not super computationally intensive, but when we transitioned over to neural nets, it was. So I think using a more black box machine learning approach is valuable. If we go, I think, to the results slide, Gwen, if you take a look at the gap between the parametric versus non-parametric approaches, it's significant. But then between one before actually, there we go. Yeah, there seems to be a pretty big gap, see over here, between, like, say, QDA and KNN. But I'm not really sure that there's a tangible difference between what we're seeing in KNN versus neural nets. So whether or not it's worth the additional computation time, I don't know that it's a huge difference, but right now, this stage of the research is not enough that it's prohibitive.
All right, one last one. Can I go one last one?
Sure.
So in the neural network, so you have a couple of layers, right? And you have input and one output, and you have one estimate, right? I was wondering what's happening in the black box. So whether it's irrelevant of what method you use within the black box to estimate your betas, right? Or it's kind of related.
So the method is called back propagation. I don't know if Dr. Becerra, he might be better equipped to answer that question of exactly how the process works.
If you want me to.
If that's all right with you.
Sure. It's a very important question. It's a relevant question, and it's the fact of the matter is that the hidden layers play a role in further training the model, and they show up as a catalyst and they disappear. That is, you can add more hidden layers with more nodes. Obviously, who's to say you only need one hidden layer? You can have 10 hidden layers, and you can have 50 nodes per hidden layer, and so forth. Obviously, the price you pay for that is more computational time and resources. The gain, I suspect, partially at least, is that you get to train the model more elaborately. That's the whole notion of let's move from neural nets to modern techniques that try to do face recognition and so forth. And so what they have done, these guys, is that they have decided the system, or they have run a code that the system decides ideally, optimally, what is the ideal number of hidden layers and what is the ideal number of nodes per hidden layer. And that is done through cross-validation. And in a way, for small data like this, you get to a point that regardless of adding hidden layers or nodes, you have saturated the model, you can't do better. The real answer is no, we don't care about the coefficients that happen inside. We just use that as auxiliary to further train the model.
Thank you, guys. Thank you very much.
Thank you.
Thank you so much. We're a little bit beyond time. Obviously, an exciting project invites a lot of exciting questions. Any other questions or comments for our students? These are students who are new to these concepts. They're just learning, but they're doing the best they can in order to start a conversation. And hopefully some of our colleagues, professors in this room, can take the work and move it to another level and make it useful. So thank you so much for coming to this presentation. I know it's a Friday and it's a big sacrifice to come to a talk like this. Thank you so much, my dear friends. I wish everyone a wonderful weekend. Happy holidays. on behalf of CCAM and everyone here. Let's thank our presenters one more time before we leave for the good job they did, and have a wonderful weekend. Thank you so much.
Thank you.
Thank you.